It's just my life is like borderline crazy right now, so I'm like just gonna think back to.
I think I thought you were done and started reading it.
No.
Because I thought you said, I'll just redo it later. I thought it's what you said, but you might finish it later. So I haven't started recreating the back.
Okay.
Oh wait, you mean the Blizzard Meet the last one? Yeah, she said that it was in the folder, which nobody took it out.
Go table 7.
Is this what it's here?
Yeah, that's what that is in your hand.
This one?
Mm-hmm. Yep.
So that's why
So if you guys put it in there and do it, then I'll add those points back to your notebook check. And it's posted on Drive if you need to use it to check your answers.
Wait a second. I'm a page off.
Okay, so we've talked about several different types of distributions. We talked about the normal distribution. Last unit, we talked about the geometric distribution and the binomial distribution. Now we're going to talk about sampling distributions. Okay. This relates back to what we did in some of the previous things, but it's a little different. So what we're doing with a sampling distribution is we're collecting a sample, and we're calculating a measure from that. When we calculate a measure from a sample, what is that measure called? So it starts with an S. Statistic. So we're taking the statistic from that sample, and we're putting it into our sampling distribution. Then we go get a new sample. From this new sample, we calculate that same statistic. We put it into our sampling distribution. Then we get another sample. We take that statistic, we put it in. So this sampling distribution is really a distribution of all the statistics. Each statistic representing a sample. Okay? In the past, we looked at a distribution being the data values themselves. Now, each value in our sampling distribution represents a sample that was collected. Okay, so that's kind of our difference. Otherwise, we treat it the same. Okay? So, we're going to get some samples. So what we're going to do is deal with some coin flips just to get some proportion samples. So what I need you to do, now listen, each person at your table, do not do this as a group. Each person at your table needs to flip a coin 10 times and calculate the proportion of heads. Then do that again for 3 trials. So each person will do 3 trials for themselves, and then I'll tell you what to do with that data once you're done with it. If anyone needs a coin, if you don't have one, this is my retirement fund. And I find coins left on the floor that goes into my retirement fund, so you're welcome to borrow from it if you need a coin.
I can now go to Walmart and buy mine's bigger though. Sometimes I realize my entire childhood has been 2 heads, 2 tails, 2 heads, 2 tails. God, 6 heads. That's how you get heads this time. You know, if I don't have to flip a coin, I gotta kill some.
You can go back and forth, see? Yeah, I got
Terrible. What happens if I catch the coin on it?
Okay, I'm going to interrupt you for just a second, and then I'll let you finish if you're still working. What I'm going to do is I'm going to come around and hand out these little green dots. So each person needs to put their initials or their name or something, because in a few weeks we're going to go back to this, and you need to be able to find your dot. So put your information on 3 of them, and then place for these 3 values up here on the chart where it says 10 flips. I'm going to put these dots under those values. Okay, so I'm going to come around and hand out the dots to the group, and then you'll record yours up on the graph. Don't mess with the data joke.
Don't put things on there. Do not. I do every time.
keep it going.
That's what one of my friends said. He said,
Okay. So, what are some observations you have about the graph? You know modal. Very good.
There's a lot in the middle.
There's a lot in the middle. Very good. Would you say it's skewed or symmetric? Fairly symmetric. We're going to come back to that describing.
discriminating, why is it symmetric? Is there an explanation for this?
Yes.
Well, we'll find out next time.
Oh, yeah. Hold that thought. Okay, so, did we all get the same results? No.
I think so.
No. We have a range of values over there that we got. And this is because each sample consists of 10 coin flips. Each of which is independent and random. So that difference between what one person gets and what another person gets is the variability in the sampling process. Okay? If you think back to first semester when we did that activity at the beginning about the jelly blubbers, remember we had that colony of jelly blubbers and we were doing our different sampling methods and we looked at how do we get a good sample? And we didn't all get the same numbers, but we got numbers that are pretty good. What our goal is here is to estimate what's the probability of getting heads when you flip a coin. And we take these values that we get and we put them all together, and from that we can see what happens most often. What is our most likely thing? Where is it centered? What can we use this to predict about what is true about coin flips? So that sampling variability, we'll talk about that. It has to do with the same things that we talked about before whenever we talked about variability. The range, the standard deviation, the IQR, those ideas of spread are going to come back in for sampling variability. Whenever we take a sample, what is the group that we take the sample from called? The population, right? We have this big population. We draw the sample out of the population. When we take a sample, we can make some calculations. We already said that calculation is our statistic. What is it we're trying to know about the population? What is that measure of a population called? The parameter. Okay? So we're using our statistic to estimate what we think is true about the parameter. So when we look at our graph, that can tell us information about our sample that we have, all of these different samples, and we can use that to make a prediction about what we think is true for the parameter, the true proportion of heads. So, here, what we have is a statistic. So each of those dots that we put on the graph is a statistic. Specifically, this would be p hat, because we're estimating a proportion. So that would be because it is calculated from a sample of coin flips. So each of us had a sample of size 10. We calculated the p hat for our sample. We put them all together, and that created a sampling distribution. So the parameter, if p hat is the statistic, the parameter is usually p, or sometimes you'll see it as pi for population proportion. But if we're describing it, it's the true proportion of all coin flips that land hits. Now, I want to make a comment on this. I've noticed whenever I give you guys a question where I'm asking you to describe what is the population, the parameter, sample statistic, one of those things, a lot of you still say proportion no matter what. It's only proportion here because we're calculating the proportion of heads. If we were calculating the weight of each coin and we found the average weight, then it would be the true average weight of coins. You want to make sure that whatever it is you're calculating is what's represented here in this statement. It's not always proportion. Sometimes it's average or mean. So be aware of that. Okay, let's look inside. So we've done 10 coin flips. We found the proportion for each one. When we put those all together, each dot on that graph represents a sample. All of those samples put together create our sampling distribution. So people get confused on, is it a sampling distribution or is it just a distribution? Sampling distribution means it's made up of lots of samples, statistics. Okay? So you take a statistic from each sample, put it together. That's our sampling distribution. So we want to describe what we see in the graph. So whenever we do that, we don't want to forget, write in context. So here we would say, instead of just saying the distribution of coin flips, we're going to say the sampling distribution of coin flips to distinguish that's what we have. The sampling distribution for 10 coin flips, that's our sample size. There's our context. So we want to talk about shape, center, spread. And if there are any outliers, we talk about that, but we don't have them. So what did we say the shape was? Yeah, so unless it is exactly symmetric, we want to say is roughly symmetric. When we have a symmetric distribution, what measures do we use for center and spread? Mean for center, what for spread? It's 2 words. Standard deviation. There we go. So normally, if it's symmetric, we use mean and standard deviation for center and spread. we're not going to go to the trouble of entering all these values and calculating standard deviation, so we're going to kind of estimate the mean. So we're going to say with a mean of about. So what do we think, what could we estimate the mean to be? What would you say is the center of that distribution? About 0.5. Okay. And for our purposes for this, we're just going to report the range. So somebody over there at table 1, what is our range here? What's the highest minus lowest? Was it 0.9 and 0? Were those? Okay. So 0.9. Okay, so our next part of this activity, we're going to do 20 coin flips per trial. We're going to record this. Anybody care to make a conjecture about what we think will happen whenever we do 20? Even more symmetrical? Somebody said it looks the same. Anybody else have an idea?
Whatever happened over there.
Thanks, Matt. Without looking ahead to what the other class already did. Okay, so we have a few conjectures. Go ahead and do your 20, and then whenever you get your proportions, we're going to record that in the second graph over there. So I'll come around and hand out your new dots. Yeah, I'll check back. I had a feeling because you had written it all out, you just didn't finish it, so I'll go back and check this.
Okay,
sorry for exploring this message. Trust, it's not how you think. It's not how you think it's going to happen. That's all I'm going to say. More or less, we actually read chapters 23 and 24. So I want to done with it.
We have a quiz today. Well, after
What do you mean it's illegitimate, Sam? How did I cheat? Look at the other classes. So many people do that. I got 80%. I don't know what to tell you. Give me a reading.
Please. And
Oh. Whatever you say. No, it's too late now. It's too late now. Do it again. Head. Rub it in the bunch. Head. Again. Head. I don't know how I got 2 high percentages in a row, but I did. 30, 35 minutes in.
I didn't do that.
My hands are filled. I'm watching the cake. Is she a grade or can't do this. I'll let you watch.
Yes, go under there.
sometimes whenever I'm thinking to myself, I feel like I'm that green dot that's in the cave by itself. Just
Okay. So, what do we notice that happened? We compare this graph with that one. The scale on the bottom is exactly the same spacing, everything. But what do we notice? That is a lot more centered. There's less variability, if we want to think of it in those terms. Is our center still about the same value? Yeah. And you will notice that will always happen. Our description, if we write this one out, the sampling distribution of 20 coin flips, still roughly symmetric. Oh, sorry. The mean of about 0.5 again. I didn't look at what the range was. Somebody over at table 1, what's the range? So the range is a lot smaller. Shape, both of them symmetric, mean about the same, but our range is half of what it was before. So it's really narrowed it down. If we compare the two, shape is similar. Center is near 0.5 for both. But the spread changed. So the range is half of what it was in the 10 coin flips. So 20 coin flips. Has a much smaller spread. If we made the number of coin flips in each sample even larger, if we did 50 in each one, you would see it decrease even more. If we did 100 coin flips in each one, it would be really narrow. Okay? So that's a question that you may see come up on either a free response or a multiple choice. What could you do to decrease the variability of your sampling distribution? You would increase your sample size. Okay? So sometimes they ask you, what would you do to make this happen? And that's how you have to think of it. Whenever you increase sample size, it decreases variability. Okay, so our whole goal is to estimate that true population parameter. And we want to get an unbiased estimate. If you remember way back at the beginning of the year, back in August, September, we talked about different types of bias that come up in a sample. We want to avoid those as much as possible. We want an unbiased sample. So it represents the value we're trying to estimate. So let's look down here at the bottom because we're about out of time. When we're talking about bias and variability, the way that makes sense to me is to think of it like target practicing. So if you've ever looked at like archery or like going to a gun range or something and you're shooting at a target. So I'm going to draw a target for each of these. And we're going to look at what does each of these mean in terms of target practice. So for our first target, we have high bias, low variability. So low variability means it's really close together. High bias means we're aiming here, but it's going somewhere else. So high bias, low variability would look like this. They're all clustered close together, but it's not where we're aiming. Okay, something is skewing this and making it go a certain way, but it's really consistent about where it's going. Okay, so there's some sort of bias that's strongly affecting it, but we're hitting the same place every time. Low bias means we're aiming at the center and we're getting close to that each time, but high variability means it's all spread out. So maybe we hit here, then down here, then up here, just kind of all around, but it's centered around the center. High bias means we're not going where we think we're going. High variability, it's really spread out. So this one may look like that. So we're always low left, but it's pretty spread out. We're not consistent about where it's hitting. This last one is what we want. Low bias, low variability. So we're hitting where we're aiming, and it's really tightly clustered. That's what we want. We want an unbiased, low variability sample. Okay, so that's where you're in your notebook. Don't forget problem set 45. That needs to be attached in your notebook right after the notes page, and complete that for tomorrow.
We need to go back and answer those.